Okay, here is the next example. We're going to solve or find a resonant frequency for this RLC series parallel combination circuit. Okay, remember one important thing. If we have only inductor in the circuit, we cannot find resonant frequency. There is no resonant frequency. To have resonant frequency, both L and C must be there in that circuit. Then only we can find the resonant frequency. Okay, and at the same time, you cannot use RLC series circuit equation or formula or parallel circuit formula, which is same. That's not going to work for this circuit because it's not either series circuit or parallel circuit. Okay, so in step 1, first we need to convert the circuit into frequency domain. So that's what I did. I did it here. Here I have 1 farad, so minus j over omega, j omega L, so which is j2 omega. And second thing is we need to find the total impedance in this circuit. So I would say this is step 2. Here is step 1. Step 1 is convert the circuit into frequency domain. Step 2 is find the total impedance looking from source point of view. Now so the first silly mistake I saw in the past, people try to use to find f naught equal to 1 over 2 pi square root of LC. This is valid only for series parallel combination circuit. You cannot use this for this circuit. Okay, if you use this formula to find the f naught in this circuit, probably I'll give you only 2 or 1 point out of 30-40 points. That's a lot of difference. So make sure that you don't use this formula to find the resonant frequency. And another silly mistake I see all the time is, say if I give 2 farad capacitor, it's going to be 1 over j 2 omega, and I saw people writing this as minus j. So 1 over j is nothing but minus j, and you know that j square is nothing but negative 1. You need to remember these things. So I saw people writing this as minus j, 1 over 2 as 0.5, and they unknowingly take the omega from denominator to numerator, and I saw lots of people doing this in the past. So make sure that it's minus j 0.5 over omega. It's not minus j 0.5 omega. Okay, those are the two silly mistakes I saw in the past. Now I'm going to find some, let me erase this so I can have enough room here. I'm going to erase this part too. Now what I'm going to do, I'm going to find the total impedance. So Z total equal to, I can clearly see these two are in parallel, so j omega L, which is j2 omega, let me put that in. So I see j2 omega parallel with 2 ohms. The combination is series with 1 over j omega. So I'm going to leave the j in the denominator itself with the omega. Okay, so this part is nothing but 2 times j2 omega over 2 plus j2 omega plus 1 over j omega. So this whole thing I will end up with j times 4 omega over 2 plus j2 omega plus 1 over j omega. Okay, now this is your Z total. Okay, so in this Z total we need to separate the real part and imaginary part. Okay, while separating the imaginary part, make sure that there is no j in the denominator. Okay, so what I can do this in this case, I'm going to keep this separate. Let me deal with this number right here, j4 omega over 2 plus j2 omega. I'm going to deal with that. So let me take this as separate. So let me say that's Zx. So that's Zx equal to, I'm going to eliminate 2, so it's going to be j2 omega over 1 plus j omega. To eliminate the j part in the denominator, I'm going to multiply this with complex conjugate 1 minus j omega. So I know that this is a plus b times a minus b. I will end up with 1 square minus j omega square. So in the numerator, I'll end up with j2 omega minus j square 2 omega square. I know that j square is nothing but -1, so that Zx in this case I have j2 omega plus 2 omega square, because j square is nothing but -1, negative, positive, divided by 1 plus j square is nothing but -1, negative, positive, so that's the reason I have positive. Okay, so now I don't have any imaginary part here. So now my z total is nothing but zx plus 1 over j omega. So I'm going to write this as 2 omega square over 1 plus omega square plus j 2 omega over 1 plus omega square plus 1 over, or I'm going to put this as minus j. I'm going to take the j to the numerator, minus j over omega. So that's my z total. Once I have the z total, what I need to do, I need to make the imaginary part equal to 0. So in this case, the imaginary part is right here. Okay, so once find the z total, to find resonant frequency, resonance frequency, both of them are same, don't worry about that wording. So to find the resonant frequency, the imaginary part must be equal to 0. So 2 omega over 1 plus omega square minus 1 over omega must be equal to 0. Okay, so now it's no longer omega, it's going to be omega naught. Okay, so 2 omega naught over 1 plus omega naught square equal to 1 over omega naught. Okay, so can I write this as 2 omega naught square equal to 1 plus omega naught square. So if I bring it out, omega naught square equal to 1, because 2 omega naught square minus omega naught square equal to 1. Okay, so omega naught equal to plus or minus 1 radians per second. So okay, that's the resonant frequency, or f naught equal to omega naught over 2 pi basically. So plus or minus 1 over 2 pi. This is hertz. Okay, so that's how we'll find the resonant frequency in this RLC series parallel combination circuit. Thank you.